Hi everyone, we're getting really close to the AP test now. I hope you're feeling that. But we're going to get started on this review of integrals. This is mainly talking about the logarithmic function. Actually, it's exclusively talking about the logarithmic function. So here we go, integrals, logarithmic integrals. So the first thing that's going to get you unstuck with all of these is that you're looking at the graph of 1 over t, or y equals 1 over t. So when you take the integral of this is one of the ways that the natural log function is often defined. It's the area under this curve is some function, and that function never really had a name. So they're giving it a name. It's called a natural log function. So for number 1, we're saying on the graph above, shade a region representing the natural log of 2. Well, if we're saying that the integral over here from 1 to x is equal to the natural log of x, then all we need to do is replace that upper limit with a 2. And when you replace the upper limit over here with a 2, what you're going to get is the area between 1 and 2, and between 1 and 2, the x-axis and the curve y equals 1 over x. Namely, you're getting this area right here. Let's see if we can zoom in over here. That area is the area underneath the curve of y equals 1 over t, going from 1 to 2. Now, this second one, on the graph above, shade the absolute value of the natural log of 1/2. And it needs to be in absolute values because area is always a positive number. And if we integrate, or if we change this upper limit, let me see. If we change this upper limit here to 1/2, that's going to give me a negative result because 1/2 is smaller than 1. So let's just write that down, or just figure that area. That area is going to be the area between 1/2 and 1. Like I stated before, the integral that we are actually evaluating is the integral from 1 to 1/2 of 1 over t. And that's going to evaluate to a negative result because the lower limit is larger than the upper limit. So because of that, that's one of the reasons why we have a absolute value here. Moving on from here, we're going to take a look at number 2, and we have, well, can I write the area shown in number 2, or in number 3, sorry. In number 3, can I write that as an integral? And that says the integral between 1 and x. So yes, you can write that as an integral. The area between 1 and x on the curve of 1 over t is the integral from 1 to x of 1 over t dt. By definition, the integral is an area. Now this one over here, if x equals 1, well, there's no area to be had. So we're integrating basically from 1 to 1 of 1 over t dt. And if we take a look at the third one, this time we're integrating from x to 1. So x is our lower limit and 1 is our upper limit. So a couple of ways you can write that, but I chose to write it this way. Negative of the area from 1 to x, knowing full well that x is less than 1, giving me an area that's less than 1, so I put that negative sign out there to balance it out. Now this next set of exercises is just basically meant to give us a workout on what does a natural log function look like, and the way I look at these is can you actually do some of the basic transformations? So natural log of x, as we know, is a function that looks like this. Okay, so the natural log function goes through 0, 1, because at 1 the area is 0. Above 1 the area is positive. Less than 1 the area is negative. So if we want to do natural log of negative x, what we're going to have to do is that is going to be a reflection about the y-axis. So notice this is the same curve but reflected through on the other side of the axis. That's what happens when you replace x with a negative x, is you create a mirror image across the y-axis. What happens then if I take where x used to be and I put a 1 plus x? Well, if you put a 1 plus x, you're going to translate that to the left 1 unit. Basically, we used to have a vertical asymptote at x equals 0. Now we're going to get a vertical asymptote when x equals -1. Okay. We used to cross the axis at x equals 1. So now in this translated version, we're crossing the x 1 unit earlier, so at x equals 0. Y is kind of like a combination of the two. Not only are we reflected, we've changed that asymptote to x equals 1. So we are reflected about the y-axis, and we have shifted, in this case, to the right 1 unit. So that's what it looks like when we shift things. I feel like this is basically a review of, in algebra, when we would learn how to shift functions left and right, up and down, etc. So now we're going to take a look at how the area and how the area is relating to the graphs of 1 over t shifted over, etc. 5a, we have the graph of 1 over t, but this time we're graphing it for x less than 0. So if you remember what the graph of 1 over t looks like when x is less than 0, it's basically in quadrant 3. I always mix up quadrant 3 and 4. I think you've seen that from me before. But we're in quadrant 3, and this time we're going from x to -1, which makes sense since x is the lower limit. It is going to be less than -1. Oh, I'm sorry, x is the upper limit, so x should be greater than -1. So this is our area. X is somewhere between 0 and 1, and the area is highlighted there in yellow. Taking a look at letter B, this is kind of just like the graph of 1 over x, only we're shifting that vertical asymptote from 0 to -1. And this time we're saying x is greater than -1, so we're looking on the right side of the graph, and that gives us this graph. As you can see, that's the same thing as the graph of 1 over x or 1 over t. We're just shifted to the left 1 unit. 0 is greater than, or our lower limit of our integral is 0, our upper limit is x. So we know x is a positive number, and that is what we're looking like. Letter C is kind of like the C above. We're taking the graph of 1 over 1 minus t. So not only are we looking at the left side, quadrants 2 and 3, we're also reflecting. So let's take a look at that graph. So in many ways, this graph is the same thing as B, just reflected across the y-axis. Taking a look, my lower limit is 0 and my upper limit is x, so x should be to the right of 0 and less than 1, so that's producing that area that you see over there. Taking a look at 6b, we know x is less than 0. This is basically the same graph as what you saw above. And I want to know what that's equal to. Well, it's going to be equal to some natural log function, natural log of t. But since we're below the axis, we have to make it negative. And another way to go around that is just to say that's the same thing as the absolute value of or the natural log of the absolute value of x. Taking a look at letter B, we'll look at the graph also. I think that's important for us to look at. This is basically the natural log, only we're shifted to the left one. So if I want to take a look at what this is going to be the natural log of 1 plus x. Taking a look at C, this time the area is going to be on the other side, so we can imagine what would it look like if it was reflected on the other side of that asymptote. And what we get is negative natural log of 1 minus x. Now the natural log of 1 minus x would be this curve over here. And if we want to go from 0 to x, that would produce a negative. So we have the negative sign there to give us a positive area this time. Okay. We're going to be moving over to number 7 here. And we're supposed to prove that the natural log of ax is equal to the natural log of a plus the natural log of x for x and a is greater than 0. By first establishing this equivalence here, this is the integral from a to ax of 1 over t dt is equal to 1 over the integral from x to 1 of 1 over u. So in order for you to do that, the first thing you're going to need to do is say, well, what if t is equal to au? Well, if t is equal to au, that means dt is equal to a du. And how will that change my integral? Take a look. The integral from a to ax of 1 over t, we're saying, well, when t is equal to a at this lower limit, when t is equal to a, then u has to equal, well, 1. And if t equals ax, you get ax equals au, and that means u is equal to x. So we've now replaced this upper and lower limit in terms of u. We've made our substitution here. T becomes au, and dt becomes u adu. Whew! Cancel out the u's, the a's, and you get that the integral from you get the integral from 1 to x of 1 over u du. Equating the left side and the right side, you get the integral from a to ax of 1 over t is the same as the integral from 1 to x of 1 over u. We're going to integrate both of those, knowing that the antiderivative of 1 over u du is the natural log of u. On the left, you get the natural log of ax minus the natural log of a. On the right, you get the natural log of x minus the natural log of 1. You know already that the natural log of 1 is equal to 0. And then with a little bit of algebra, you can see that the natural log of ax is equal to the natural log of x. Or, sorry, natural log of a plus the natural log of x. Let's take a look at number 8. Use the definition of the logarithmic function to write a differential equation that has y equals natural log of x as a solution. Well, that's pretty easy, I think. There we go. The derivative dy dx of some is equal to 1 over x. When we integrate that, that should give me natural log of x, or y equals natural log of x. Letter B, find the general solution to that differential equation. So let's find our general solution. First, we separate our variables. And then we take an antiderivative of the left side and the right side. Of course, the natural log of dy is y, and the antiderivative of dy is y, and the antiderivative of 1 over x dx is the natural log of x. So there is my general solution. Moving on to number 9. Write the differential equation that has y equals 2x as a solution. Sorry, y equals natural log of 2x. We want that to be a solution. And compare your answer and explain what you found. So take a look at that natural log of 2x. We just proved that the natural log of 2x is the same thing as the natural log of 2 plus the natural log of x. So basically, the differential equation is the same differential equation that you got in question 8. dy dx equals 1 over x. Cleverly, you can say that the c is natural log of 2, since natural log of 2 is a constant. And then your solution becomes y equals natural log of x plus the natural log of 2, which of course is the natural log of 2x. So that's all our natural log fun today. I hope you guys enjoyed that, and I will see you next time.